When you get right down to it, science has its own language. It's not English or French or Mandarin. It's the language of measurement. It's how scientists across the globe actually communicate, compare notes, and build on each other's discoveries.
But what if that language wasn't universal? I mean, just imagine trying to build something incredibly complex, like a Mars rover, where one engineering team is using inches and another is using centimeters. It's a recipe for absolute disaster, right? Without a shared, standard system, you're pretty much guaranteed chaos.
And believe it or not, for centuries, that's exactly the problem scientists were up against. If they were ever going to truly collaborate and push our understanding of the universe forward, they had to agree on one single, coherent way of measuring things. They needed a universal language.
So, to really appreciate the solution they came up with, we first have to understand just how messy the problem was. Let's take a quick look at the world before there was one single standard.
I mean, just look at this. And this is just a few of the systems that were floating around. You had the CGS system, the British FPS system, the MKS system. Sure, they all kind of agreed on the second for time, but for basic things like length and mass, it was a total free-for-all. This kind of confusion was a massive roadblock for scientific progress.
So how do you fix a problem like that? Well, you create a universal alphabet that every single scientist, no matter where they are, can learn to speak and write.
And that solution, the one the world agreed on, is the, and forgive my French here, the Système International d'Units, or as literally everyone calls it, the SI system. This became the official language of science, the fundamental set of building blocks for every measurement we make.
At the very core of this language is the idea of a base unit. The best way to think about a base unit is as a fundamental letter in our scientific alphabet. It's a single basic measurement for a core physical idea like length or time, and you can't break it down any further.
And here it is, the entire alphabet. It turns out there are only 7 base units in the whole SI system: the meter, the kilogram, the second, the ampere, the Kelvin, the mole, and the candela. That's it. Every single measurement in the world of physics can be traced back to some combination of these 7 fundamental letters.
Okay, so if the base units are the letters, then what are the words? Well, those are what we call derived units. We make words by combining the letters, right? Same idea here. Speed, for example, isn't a base unit. It's a word that we form by combining length, that's meters, and time, that's seconds, meters per second. It's simple, it's logical, and it's incredibly powerful.
But just knowing the alphabet and some words isn't enough to be a good communicator. You also have to use punctuation correctly. And in science, our punctuation is what tells everybody else exactly how precise our measurements really are.
We do this with something called significant figures. And I know what you might be thinking, sig figs from high school chemistry. But this isn't just some tedious math rule. It's actually a form of scientific honesty. It's how you tell anyone reading your work which numbers you're totally sure about and which one is your first best guess. So how does this work? The rules are actually pretty simple. First, any digit that isn't a 0 is always significant. Easy enough. Second, any 0 that's sandwiched between 2 non-zero digits, that one counts too. The only tricky ones are the zeros at the end. If there is a decimal point anywhere in the number, like in 3.500, those trailing zeros are significant. But if there's no decimal, like in 12,300, they're not. They're just placeholders. Okay, now what happens when you have to do math with these numbers? This is where people get tripped up because the rules are different for different operations. When you multiply or divide, you look at the total number of sig figs in your starting numbers. Your final answer can't have more sig figs than your least precise measurement. But when you add or subtract, you ignore the total sig figs and you only look at the number of decimal places. Let's take a real-world example, like finding density. You divide mass by volume. So here, our mass has 4 significant figures, but our volume measurement only has 3. That means our final answer must be rounded to 3 significant figures. Your calculator might spit out a crazy long number, but you have to report it as 1.69, because claiming any more precision than that would be scientifically dishonest.
All right, so we've got our alphabet of base units, our words of derived units, and our punctuation of significant figures. Now for the most powerful tool of all, a way to check if our scientific sentences, our equations, actually make any logical sense.
Now really, just think about that for a second. Is it actually possible to check if a physics equation is valid without plugging in a single number? It sounds kind of like a magic trick, but it's a fundamental tool that physicists use all the time.
It's called dimensional analysis, and this is the ultimate grammar check. The idea behind it is actually really simple. Whatever's on the left side of the equals sign has to have the same fundamental dimensions, the same combination of mass, length, and time as whatever's on the right side. You can't say an apple equals an orange, and in physics you can't say energy equals velocity. They're just not the same kind of thing.
Let's see it in action with a classic physics equation. On the left side, we have kinetic energy, which is the energy of motion. And on the right, we have potential energy, the energy of position. Are they dimensionally the same type of thing? Let's find out.
Okay, let's break it down. On the left, mass is just m, velocity is length divided by time, or L over t, and we have to square that. So that side simplifies to m times L squared over t squared. Now for the right side, mass is m, g is acceleration, which is length over time squared, and height is just length, L. You multiply that all together, and what do you know? You get the exact same thing.
The dimensions match perfectly. So, without even thinking about numbers or doing a single experiment, we've shown that this equation is plausible. It's dimensionally consistent. It passes the grammar check.
So let's zoom out and pull all these pieces together to see what mastering this language really lets us do.
And that's really the whole system right there. Science speaks a language built on a simple alphabet of just 7 SI base units. It uses the punctuation of significant figures to be honest about how precise it's being. And it uses the powerful grammar of dimensional analysis to make sure that its sentences, its equations, are logical and consistent.
And look, this isn't just some neat idea that academics talk about. This is the official, internationally accepted standard for science, for technology, for industry, all across the entire planet. It's the framework that makes all of modern science possible.
But here's the coolest part. This language isn't set in stone. It's a living thing. It evolves. In fact, the official definitions of these base units were just updated in 2018. They did that to make them even more precise by tying them not to physical objects, like an actual chunk of metal for the kilogram, but to the fundamental, unchanging constants of the universe itself. As we get better at measuring things, our language has to get better too. It makes you wonder, doesn't it? Which letter in our scientific alphabet do you think will be the next one to get a rewrite?